Okay. Good afternoon, everybody. My name is David Litchfield. I'm the Managing Director of NGS Software, although my other title is Chief Research Scientist, and in that capacity I'm here today talking to you about Oracle Backdoors, otherwise known as rootkits. The reason I've very recently been looking at rootkits again is because I'm moving more into forensics, database forensics these days, and I'm interested in trying to work out whether there are any things that can be done to help detect for things like backdoors, and eventually get to the point where you increase the technology to the point where these things almost become undetectable. And one of the examples we'll be looking at today is an in-memory backdoor that essentially changes some data, specifically the password hash for the system user, such that anybody can then log on, provided they know what the new password is going to be. So it's essentially because you're not hooking any kind of function or changing any code in memory, and you're changing data that is there to be changed, it's going to be very difficult to protect against, basically. So database backdoors or rootkits are really nothing new. In 2001, NGS Software, the company I work for, warned of a potential backdoor in SQL Server that basically you change the X status of one of the user accounts and you could still log on. So it essentially looked like this was a group user, a group, but essentially it turned out to be a user who could log on with full privileges and so on. Chris Anley then moved further on into database backdoors. He wrote a paper called Violating Database Enforced Security Mechanisms, and essentially it covers runtime patching. It essentially hooks there's a function called f has object permissions that basically looks up the UID of the user, and if that user ID returned is 1, then no permissions checking is done. So the actual compare is patched essentially, so it always returns the effective user ID as 1, so that permissions checking is essentially disabled. And then in 2002, a couple of days later in 2002 actually, as part of the paper that I presented at Black Hat, that eventually had the code in it to exploit the SQL Server name resolution service that eventually was exploited by the Slammer worm. In there I also spoke about Trojaning extended store procedures and start procedures and everything like that. Then Database Hacker's Handbook that myself and a couple of other colleagues wrote at NGS Software. We warned about the dangers of trusting views when doing audits of database servers, simply because views can't be trusted. Most recently, Alexander Kornbrast has been speaking about hiding users and processes, and then last year at Black Hat in Oracle Rootkits 2, he brought up an interesting, of his talk, the most interesting topic there, I believe, was pin procedures. What pin procedures basically means is essentially you can lock in the Oracle SGA the code of some PL SQL packages, basically. So you can manipulate, modify the package, lock it in the SGA, and then change the code back again, so that if anyone comes along and does an audit of the procedure, like for example, compares the checksums, then the original checksum is there, but the one in memory is actually the one that takes precedence. So that was an interesting attack. The problem is current rootkits are trivial to spot. So I'm asking the question here, if we've got all this stuff on database rootkits, what's the point in having a talk today, nearly 5 years after the topic was originally broached? Why continue talking about database rootkits? Well, current rootkits are trivial to spot. We've solved that problem. We can, find these things really easily. What about the next generation of rootkits? And indeed, in Alexander's talk last year, he alludes to third generation toolkits that basically, modify data and so on to allow access. Now, Alex's talk didn't really present any third generation rootkits. So today, that's what I'm going to present today. Basically, is present a couple of third-generation rootkits that demonstrate what can be done. So before getting to that, let's look at some of the current backdoors or rootkits. I mean, some people might break into a database server and create themselves an account which they can then come back to and log into later on. Now, obviously, anybody doing an audit of the server will come along and select from, say, for example, DBA users and see this account called hacker or whatever it happens to be. The point is a DBA who is on the ball will recognize that there are accounts on a system that really shouldn't be there. So the next step to that is basically, hiding, modifying the view such as DBA users and all users, so that when someone comes along and does a select username from DBA users, the account name is essentially hidden. Other methods of backdooring, Oracle. Oh, well, actually, before we talk any further, this isn't just applicable to Oracle, by the way. This is across the board as far as all database servers are concerned, or in terms of the ramifications. But in terms of the specifics, obviously, we're dealing with Oracle here. So modify some PL SQL packages. Trivial to do, especially if you have an unwrapper. There are a couple of unwrappers floating out there, but essentially you unwrap the code, make your modifications, and rewrap the code and upload it again. Now, obviously, trivial to spot again because the checksum of the PL SQL package has changed itself. Other ones there are some dangerous PL SQL packages that, for example, take a string and executes that string as straight SQL. Now, a lot of the sysowned packages will do that. I list a number of them in the Oracle Hackers Handbook. The idea is basically if you lose access for whatever reason, then or you lose your DBA privs if you've given yourself DBA privs, you can go around giving yourself these privs again by executing one of these PL SQL packages. Modify or create after logon triggers, so every time someone logs in, you can check whether the user has the requisite permissions. If they do, you can go and do execute some nefarious code. And again, the same with startup procedures, or indeed going all the way to modifying binaries. Now we'll look at a couple of examples of these and why they're, in terms of implementation, so well, not poor, but easy to spot, and how they go about themselves. So modifying views, so along comes a user, creates himself an account called hacker, and he wants to hide the fact, so they'll modify the view of DBA users and all users so that the hacker account isn't displayed. Because it's modifying an object in the data dictionary, this is trivial to spot. One of the aspects of this is checksumming the code of the view and then comparing that later on is not the right way around, to check for modifications. Because at the end of the day, you're trusting a database server which may have been compromised. So it's, if the attacker's, that advanced, basically, they can modify the database server such that when someone does a check on the code of the view, for example, they might use the dbmess utility package to create the checksum. Then they just need to modify that and fire back whatever they want you to see, essentially. So essentially, you need to go to the data file itself, extract the view body from that, and do your checksumming on that directly. Another way of not worrying about the views problem is essentially just use the underlying table itself. Rather than relying on DBA users, just use the sys.user table and so on. Now, a very nice, simple way of checking whether someone's actually manipulated the DBA user's view, for example, is using the minus operator. So I'm just going to change the view for a second here, so that an account called Hagsaw is not shown. If we see there in the bottom right-hand corner, essentially we're modifying the view there so that if the user Hacksaw is displayed, is there, don't show it, essentially. So if I actually go ahead and create that user first, connect/ssdba, create user Hacksaw identified by password. grant create session to XOR. Okay, so if we do a select username from DBA users, username equals XOR, we can see the user exists. So we modify the view essentially so that, now obviously this requires the requisite permissions, but we can do this through, for example, PL SQL injection vulnerability. There's a number of them. So the next time we run that query, no user exists. So the thing is, if we compare those two, if we select from users where type is 1, in other words, a user, and we select from username where from DBA users, if there's any rows returned, then that says there's a difference between the underlying view and the underlying table and the overlying view. So that indicates that there is indeed a problem with DBA users. So that's been changed. So that's just using the minus operator. We, of course, when we're doing an audit, rather than using DBA users and having to worry about that, just use the underlying table essentially. So if I just change that all back again. Okay, so if we then go back and redo this, there should be no difference between the two. So no error selected, so that's good. So our hacker account should exist again. So select username from DBA users, order by 1. So there we go. So it's visible again. That's good. Okay. Okay. So you get the idea. These are trivial to spot. We just check some of the code of the view, or just use the underlying table essentially. So rather than actually modifying the view itself, another way of achieving the same thing actually is exploit the view contents instead. Now, what do I mean by that? Well, if we look at the text of the view, there's a whole bunch of predicates down here. Oops, excuse me. These are the predicates here, essentially the where clause. So if we get rid of that. Now, all we need to do is essentially pick one of these things and make it not true, and ensure that we can still log in with that account. So for example, if we look at this row here, where u.dataTS number is the same as dts.ts number. That's essentially looking at the default table space and everything like that. Well, if we choose a table space that doesn't exist, this DTS, by the way, do we have a laser pointer, by the way? No? Okay, it's not worries. I'll just highlight it here. This DTS here is essentially taken from there. So if we modify the user directly, so he has a data.ts. Oh, great! Thanks very much. Remind me to give it to you back at the end of time. How does this work? So essentially, in here, if we choose a table space number that doesn't actually exist, and we'll do this. So here we're going to set the data TS in the user table to 1337. One row updated, commit that. If we select username from DBA users, where username equals XOR. No rows are selected essentially, and that's because here, when that view is essentially called, this is no longer true. So the username Haxor isn't returned. So just verifying that. Order I1. Because in this case, obviously there is no table space name with a number of 1337. So if we then go back and modify that to say 4, which is a table space number that does exist, commit that, and then rerun the same query, we can see it's back again. Okay, so rather than modifying the text of the view, I mean, we can simply just manipulate the view itself so that it's disappeared. Now, I say this is a new method. It's not really new. This is exactly the same thing in Oracle that we did with XStatus in SQL Server. It's essentially abusing the view's content itself to make it, the account hidden. And of course, we can still use the underlying table user dollar to find user accounts. So it doesn't solve any problems as such. It's just, rather than changing the view of the text kind of thing, which is going to be easily noticeable, just modify do a direct manipulation of the data TS number, for example. Okay, modifying the binaries. From Alex's Oracle Rootkits 2.0, add the account, make a copy of the user table, and call it ASER, $, drop the account, stop the server, look for all occurrences of user $, and change it for ASER $, restart the server. Now all logins are now consequently read from this table. And so when the DBA looks at user $, he thinks, okay, I can't trust the view, so I'll look at user $, instead. The account is not visible. Well, there's a lot of hoops to jump through there, obviously. But one of the obvious reasons this will be easily spottable is the next time the DBA adds a new user account and does a regular check on user $, he'll be like, well, wait a minute, I just added an account. Where is that account? It's not showing in the user table. It sticks out like a sore thumb, as does the presence of a new data dictionary object, as does shutting down and restarting the database server. If your DBAs don't notice that, you should fire them and get new DBAs, kind of thing. And of course, we can check some of the OS files themselves. Again, improving the method. Why? Essentially, the object here is to have a user account that's not visible from the user $, table. So, can we do anything to, achieve the same ends without actually having to modify the binary? Well, of course we can. Otherwise, I wouldn't be speaking about it. So, if we, for example, do a create user Haxor2 identified by password. Grant create session to Haxor2. If we then connect as Haxor2, and then reconnect as sysconnect sysdba. If we then delete from user $where name equals Haxor2 0. Okay, one row deleted, commit that. Okay, now if we try and log, because we've essentially deleted that user, we've not dropped it, we've deleted the user. Can we still log in with it? And of course, /password. So we've deleted that user, but we can still log in with it, essentially. So the thing is, if we then reconnect, or if we go select username from all users, order by 1, we can see that our Haxor account is in there, obviously, but our Haxor2 account isn't there. That's because we've deleted it from the sys sys.user$table. So essentially this achieves the same ends as modifying the binary. We hide the account from user $, but essentially this account is in the SGA. It's still in the SGA and available to be logged on because we've just done a direct delete from the user $table. So whilst it's more practical, because obviously you don't need to shut the server down and everything like that, the point is this will not survive a server restart. So the attacker needs to reinfect the server if it's ever stopped. But given that it's a database server and database servers are very rarely stopped, the user, or the attacker rather, has a good chance of their access being there for a long, long time. The way I see it, if you can modify a binary though, why not just patch the code so that if there's a user called, if someone attempts to log in with a username of Hags, or whether it exists or not, just log them in anyway, kind of thing. That to me is the easier way of doing it, because that way you don't have to create, arbitrary objects in the data dictionary. So, third generation rootkits. In-memory backdoors, basically, these are the things that Alexander, alluded to in his talk last year. So what are our options? Runtime patching of code. Well, Chris Anley did that kind of thing in 2002. So we won't repeat his efforts here, but we'll obviously talk about, at the end of that, looking at ways of, catching attempts to patch code at runtime. Obviously, we could change entries in the import address table. When an executable loads, or a DLL for that matter, and it requires to import functions from other DLLs, then the addresses are stored in what's known as the import address table. Now, and these are then dereferenced when they're called. So obviously, if we can manipulate these, we can redirect flow of execution. The other one, which is what we're mainly going to be concentrating on, is the manipulation of data. Data that is supposed to change, so in terms of watching for attacks against it, it's going to be much more difficult. Then we have to look at delivery mechanisms. How do we get our in-memory backdoor loaded? We'll look at external processes, network or libraries over the network, DLLs over the network. Or, for example, which is probably going to be the most easiest and most common attack, is either a buffer overflow, whether it be stack-based or heap-based, format string bug, or the kind of write a D word of your choosing to anywhere of your choosing kind of premise. So if we look at external processes as a delivery mechanism, we could use external procedures, for example. Call the system function to load an executable over the network. That executable would call open process on the Oracle process. Virtual allocx, this is obviously on Windows, by the way, if you're wondering. Call virtual allocx to allocate memory in the Oracle process. We need space for the stack and the code itself. We then write into the Oracle process using write process memory, and then create remote thread. But basically what we do is point the thread to the beginning of the code section. And then off it goes, and you can do whatever you want to do. You can do the same things, obviously. We can run executables from the Oracle JVM, but if we're running, the Oracle JVM is built into the Oracle process, by the way. So we'll look at, that's a bit redundant in a way, because, well, we'll come to that in a minute. We could call DBMS scheduler, or we can modify the PLSQL compiler flags. And the make utility, we can set that to an executable, and again do the same things. Or we could load a DLL from the Oracle JVM, again, which, as I said, is internal. So this is why it's like, why do you need to load an executable just to achieve the same thing? Because we're already in the process anyway. We would call system.load, and it allows us to do whatever we want, obviously, once that DLL is loaded. So as a quick demonstration of this, this is just a simple DLL that exports, some functionality. It's a memory manipulator, basically, and a shell server. So once we're, have our requisite DBA privileges, basically, we can then essentially go around setting out, creating a Java class that will load a library for us. We then wrap a procedure around that and execute that. So this will load over the network. I'm hoping it will anyway. Might take a moment. Well, not might, it is taking a moment. Whilst that's going on in the background, I can't really talk about the next thing because until this demo's over. Come on. Yep, got an IP address. Oh, right, back in business. Okay, so PL SQL procedures successfully completed. If we then look at the DLLs list, DLLs, oracle.exe, we can see that it's loaded into the Oracle address space, the shell server listener.dll. Now, that there is its base address. So we can manipulate this contents of memory. So if we go star dump the next 10, oops, I need a host name, Apollo. So this basically, you know, takes an address and dumps memory from that, so we can inspect memory. This here is the beginning of the, you know, the DLL we've just loaded essentially, and this here is MZ and so on. You know, the PE header basically. So we can then change that if we wanted to. Not that this buys us anything, but we could change this to 41, 41, 41. So if we then look at that, we can see that we've written memory in the Oracle process essentially to 41, 41. Now what we could do is use this to cycle through memory looking for interesting things and change that to suitable values. Or to show you what else the shell server does, it's really crappy but a lot of fun. On port 1337 is a shell server essentially. So, you know, we can run commands and stuff like that. So that's all this DLL or backdoor does. It allows me to poke memory and connects me to a shell if I want it. Really crappy, but it does the job. Okay. Buffer overflows. Okay, these are probably going to be the simplest attack because obviously if the remote Oracle server can get back out to me over, you know, the network, then there's real problems with egress filtering on the firewall. They shouldn't be able to do that. So in terms of delivery, if we can exploit a buffer overflow, we can pretty much load up everything we want from there. So the example we're going to show here is exploit a buffer overflow, an extant buffer overflow in Oracle. It looks for the password hash for the system user, and it does this by calling an Oracle function that essentially hands me back some user structures in the SGA, and once it's found the password hash for the system user, it changes it to a known hash that essentially is a password for secret. So the way it works is basically we need a handle to the SGA stuff first. Now these are hard-coded for this version of Oracle, but obviously you know, to make it useful across all versions of Oracle, then you need to avoid the hard-coded address problem. But essentially, at this stage here, we've essentially got the handle to the beginning of the user structures essentially. Once we've got that, we see we push EAX there. Eventually, going back, we're left with EAX and pointed to that there. We push that onto the stack, and then load some other stuff up. Here we have the user we're interested in is 5 for the system user. So we load into EAX the effective address of the base pointer plus OX1C, and then we write 5 to that value, push EAX, push 7, move into EAX the value of, the address of the function we want to call. That's actually in the Oracle executable itself, and then we call it. Now, I got this address by disassembling the authentication procedures essentially, and looked at what it did and thought, well, actually, wait a minute, we can hook into that and basically, manipulate the password hashes. So once we call EAX, essentially, we should have a pointer back to the user structure for the system user. We then make some modifications to that. So OXC2 bytes into the structure, we get the beginning of the password hash. So this here is the password hash. And that's the password hash for the system user when it has a password of secret like that. So we then write that into, we overwrite the extant password hash essentially there. The vector I'm using here happens to require that the exploit be written in ASCII, so this needs a bit of explanation. The exploit I'm going to be demoing, because it has to be ASCII, I've written an ASCII, where's this? A decoder, I've written the decoder writer in ASCII. So the exploit, when it begins, has the decoder writer, a buffer, a destination for the decoder when it gets written out, and the encoded exploit. So when the decoder writer executes down this way, it starts writing the decoder out this way. So eventually, the two join. And when the two join, execution continues from down here onwards. Whoops. And obviously, the decoder, all that does basically, it loops decoding this stuff here. And eventually, the decoder finishes, and we continue execution from there onwards, kind of thing. So that way we can get our arbitrary code across without having to worry about, there being like characters greater than 7F, OX7F kind of thing. Okay, the decoder itself. Essentially, when I encode the exploit, I take a byte of exploit, split it into 2, the most significant 4 bytes and the least significant 4, not bytes, most significant 4 bits and least significant 4 bits, add 41 to each half, essentially, OX41 to each half, and then that becomes our encoded exploit. So decoding that exploit is the same in reverse. Essentially, we set ESI and EDI to point to the beginning of the encoded exploit, move the byte into the AL register, subtract 41 from it, shift it left 4 bits, and then increment the pointer to the next byte in the list, add that to the AL register, subtract 41, and eventually we're left with our original byte of real exploit code, our actual exploit code in AL, which is then written to ESI. We increment the pointers and keep on going, and until we come across this either a Q or more. So it's that essentially is our equivalent of our null terminator, but it's not a null terminator. It's if it's Q or more, stop looping. So otherwise, go back and loop up to there. So because these slides will be available offline, before doing the demo, I've obviously got some screenshots, which I'm obviously going to do this live, but for those people who aren't going to be here, there should have been another slide in there. I must have deleted it. We can see here, we'll be logging on as manager. That works. Connecting as secret fails. You're no longer connected to Oracle. Now I've redacted the actual vulnerable function itself for those people who will be reading it later, because it's better to go that way because I don't want to be handing out real live exploits. And afterwards we try and log on with our old password. It doesn't work anymore, but we log on as secret. So demonstrating this. Now you guys are obviously going to get to see it because I can hardly redact it in front of you. But if we connect Scott/Tiger, if I show you here, if I connect system/manager, we're connected. If I obviously try as connect with secret, invalid username or password. So if I now, this is the actual code. Let me walk you through this. So essentially what we're doing here is filling up the buffer here. X is our buffer, essentially. We overwrite the save return address. Well, actually, we're overwriting the exception handler here, to be honest. I should fix that. And we're overwriting it with this value. This value exists in oracle.dll. There is a pop-pop-ret at this address. This here is obviously the ASCII equivalent of it there. Some more bytes. Oh, we have to have a short jump up here. Basically, this jumps us over the address, basically, when we're in memory. We need to adjust ESP correctly for this to work. And this here is our ASCII armored shellcode decoder. This here is the buffer where it all gets written to. So that's where our decoder is written to. And this here is the encoded backdoor. Funnily enough, it starts with jail. It's like, don't use this, otherwise you will go to jail. That's just completely coincidental. And here is the termination. This could be Q, for example, or more. And then we execute the function. Now, because this actually itself calls terminate thread on the thread itself to continue to continue execution. It's going to hang in this window. So it's hanging now, but this should have changed the password hash to secret. So if I go one up there and hit enter, I'm now connected. So all that's done is basically, as I said, called an Oracle function that's returned a handle to the user structure for the system user. We've overwritten his password hash in the SGA with the known hash for that which would equate to secret and gain access. So the idea there is obviously in terms of detection, runtime patching we can detect quite easily because we can hook calls to, for example, say virtual protect X or virtual protect. So if anyone tries to do any runtime patching of code, because code is loaded as read-only, if we don't have code which is code pages which are writable, then we're going to have to call this. And by default, they're not writable. So if we hook this and make sure the call is coming from known safe locations and so on, then if someone exploits a buffer overflow to call virtual protect X or virtual protect, then we can monitor access for that and so on. And again, changes to the import address table, they're quite easy to spot too. Easy relative to the problem of changing data. Changes to data that are supposed to be changed, for example, the password hash of the system user. Well, sure, we can go ahead and protect that area of memory, watch it for changes and everything like that, and alert if there are any changes and say we may have been compromised. Well, what about the next thing? We can't go around protecting every bit of data that has some relevance to the security of the server, because eventually we'll be using up so much processing time that there'll be no processing time left to service database queries. So this is a real problem. How do we protect against this? Well, if someone can come up with a solution, a light solution for that, then that would be wonderful, and you could probably make millions of pounds from it, or euros rather. Currently, I think the best thing you can do is keep your servers locked down and watch for abnormal activity. So, any questions? No?
We have still 10 minutes for questions.
Sure. Sure.
What is Oracle doing about it right now?
Well, there's nothing wrong with this. I mean, at the end of the day, once you're running code through a buffer overflow, for example, then you're running code at the end of the day. It's not like you can do anything to protect against these things. Or if you do own the server with sys privileges, you know, it's like, well, you can do anything you want anyway. So it's not really an Oracle problem, to be honest. Once you've got the keys to the kingdom, you've got the keys to the kingdom, you know. So in terms of protecting against things like new flaws as and when they come up, well, they're taking steps to remediate new buffer overflows or SQL injection flaws all the time. So. But it's not, Oracle's done nothing wrong here, by the way, nor if this was applicable to SQL Server or Postgres or MySQL, no database vendor is at fault here. It's just simply, once you own it, here's stuff you can do to retain access at a later date kind of thing. So, no other questions?
Hey,
sure.
When the real admin then logs in again, next time, you change it to secret and then revert it back under to the old.
Yeah, well, we could repeat the exercise and change it back to, the old password hash, essentially.
And then you have two processes hanging there? Or?
Well, no, it's not. It's no longer hanging. This is on. This SQL Plus is hanging on my machine, the attacker's machine kind of thing. And as far as the remote server's concerned, the thread's just terminated kind of thing. So as far as it's concerned, the client's disconnected kind of thing, and that thread's torn down. So, yeah, it's just SQL Plus doesn't recognize that the thread's terminated on the remote server. It thinks it's still there kind of thing. And it's waiting for a response coming back.
Since you changed it in memory, if it's rebooted, the old password reverts.
Correct.
So if you're sneaky, change it.
Could you repeat the question so it's in the audio?
Well, the thing was, have you got the mic there?
Yeah. I was just saying that since it's only changed in memory, if the system's rebooted, it reverts, and then if you're clever, you just change the password, log in, and change it right back.
Absolutely.
And the only way you're saying you'd notice any of that is if you're hooked one system call that you're using.
Sure, we could hook this function and everything like that and make sure it's coming from a verifiable source, for example. But at the end of the day, we can modify something else that has security relevance. For example, we could change the fact that it's the bits that say whether you're a DBA or not. For example, we flip a 0 to a 1 or a 1 to a 0, whichever happens to be. So we protect against that, and we protect against this, and eventually we've got this whole long list of things we protect against. And as I said, you can't really do that with a database server, because for every 1,000 things you think of protecting, there's going to be another 3,000 which you're not protecting, and we can still use. It has the same equivalence kind of thing of achieving the same thing. But yeah, I mean, once this server's stopped, and we would need to reinfect it again, obviously. So it obviously would have to depend on the target environment, whether they apply patches or not. If they don't apply patches, then your initial vector, reinfection vector, is still going to be there kind of thing. So, no other questions? Great.